Hello, Meteor.
Hello, Meteor.
Have you heard about the website called Discovery.com?
Discovery.com is my guidebook for life. I learned how to plant an herb garden, train my dog, and cure my dandruff.
I learned that most meteors burn up in Earth's atmosphere. Ah! The atmosphere! Ah!
The atmosphere! Oh!
Welcome to Short Planetary Geological Essays, narrated by Daniel Hutchinson. Martian Sand Dunes. We will begin by delving into the intricacies of a sand dune, a landform composed of wind and sometimes water-driven sand. Taking the form of a mound, ridge, or hill, areas where many sand dunes are found to congregate is called a dune system, complex, or field. Sand dunes can occur in different shapes and sizes, but most kinds of dunes are longer on the upflow side, also called stoss, where the sand has been pushed up the dune, and having a shorter slip face on the leeward side of the dune. The valleys or troughs between sand dunes within a dune field is called a dune slack. Sand dunes are most commonly found in desert environments and seashore beaches. The lack of moisture in the air hinders the growth of vegetation that would otherwise interfere with the development of sand dune formation. Some coastal areas can be found to possess one or more sets of dunes that run parallel to the shoreline, located directly inland from the beach. These dunes protect the land against the ravages of storm waves from the sea. The makeup of sand dunes are sand-sized particles and can consist of quartz, calcium carbonate, gypsum, or other materials. 6 types of sand dunes are classified by geologists. They are dome, linear, parabolic, star, transverse, and barchan. Sand dune areas may occur in 3 forms: simple isolated dunes of basic type, compound larger dunes on which smaller dunes of same type form, and complex combinations of different types of dunes. Starting with barchan dunes, they are crescent-shaped mounds that are wider than they are long. The lee side slip faces are on the concave sides of these type of dunes. Barchan dunes form under winds that blow consistently from one direction, known as unimodal winds. When there is only a small supply of sand, barchan dunes will form separate crescents. When there is a greater supply of sand, they start to merge into barchanoid ridges, and then from there evolve into sinuous transverse dunes. Sinuous transverse dunes lie transverse or across the wind direction, with the wind blowing perpendicular to the ridge crest. Next are the seef sand dunes that are linear or slightly sinuous. They are called seef dunes after the Arabic word for sword. Seef dunes are associated with bidirectional winds. Being radially symmetrical, star dunes are pyramidal sand mounds with slip faces on 3 or more arms that radiate from the high center of the mound. They tend to accumulate in areas with multi-directional wind regimes. Star dunes grow upward rather than laterally. They may occur around the margins of sand seas, particularly near topographic barriers. Oval or circular mounds that generally lack a slip face. Dome dunes are rare and occur at the far upward margins of sand seas. U-shaped mounds of sand with convex noses trailed by elongated arms are known as parabolic dunes. These dunes are formed from blowout dunes, where erosion of vegetated sand leads to a U-shaped depression. The elongated arms are held in place by vegetation. Sometimes these dunes are called U-shaped, blowout, or hairpin dunes, and they are all well known in coastal deserts. Unlike crescent-shaped dunes, their crests point upward, with the bulk of the sand in the dune migrating in a forward direction. When it comes to sand dunes, they are among the most widespread aeolian features to be found on the surface of Mars. Martian sand dunes serve as unique indicators of the interaction between the Martian atmosphere and the planet's surface. On Mars, sand dunes form and accumulate where a supply of sand-sized grains exists and is carried downwind by a geological action known as saltation. Deposition of the sand grains begins at the point where these winds weaken below the threshold for the sand's ability to be transported. The result for planetary geologists is the study of Martian dune processes that contributes to both Martian atmospheric and sedimentary science. When noticing the presence and observing the morphology of Martian sand dunes, planetary geologists note the dune's sensitivity to subtle shifts within the Martian wind circulation patterns and strengths, which are influenced by changes within the planet's orbital parameters. The spatial distribution of the Martian aeolian sand relates to patterns of sedimentary deposition and erosion of source materials, giving clues to the sedimentary history of the surrounding terrain. Martian sand dunes are particularly suited for comprehensive study by planetary geologists because they are abundant on the Martian surface over a wide range of elevations and terrain types. Martian sand dunes serve a dual purpose in the further understanding of both Mars's climatic and sedimentary processes, the two currently fundamental topics of Martian science. On October 5, 2020, planetary geologists announced the discovery of a group of 1 billion-year-old Martian sand dunes in the planet's Valles Marianas region. This rare find gave planetary geologists a second big discovery as well, that the climate, atmospheric pressure, and landscape evolution on Mars has remained relatively consistent over the past billion years. Not only do planetary geologists understand what Mars was like a billion years ago, but of how the red planet's climate has evolved over time. The evidence observed included both lithification, the process by which loose sediments are compacted into solid rock, and the burial of those dunes by wind over time. These Martian paleo sand dunes have been untouched by the same processes of geological forces such as plate tectonics and erosion by wind and water that have altered Earth's surface over the past billion years. Attempting to date planetary surfaces by planetary geologists is extremely challenging without physical samples. The accumulation of impact craters on the surface of Mars gives an estimate of the surface age, with older surfaces accumulating more impact craters. These deposits did not show many craters, indicating they must be relatively young. Erosion rates were observed at or how quickly landforms are worn away by wind and other factors. Using these two techniques, it was estimated that these dune deposits to be no older than a few billion years, or they would have accumulated more craters, but not younger than about 1 billion years, or erosion would have erased them from the surface. Planetary geologists have observed modern Martian sand dunes in the area that are orientated in very similar directions to those of the paleo dunes. This indicates the major wind directions that are responsible for the sand dune shape have not changed substantially over time. Also observed are very similar sized and spaced sand dunes from the two time periods. This indicates the atmospheric pressure hasn't been significantly different either. Thus, Mars of a billion years ago was pretty much like the Mars of today, at least as far as wind patterns and atmospheric pressures are concerned. I hope you've enjoyed this short planetary geological essay about Martian sand dunes, and thank you for watching.